Hello, everybody. My name is Andrés Escala, and this is the title of my talk. Massive black hole formation has been studied that has several paths to form black holes that in the recent years have been, through simulation, narrowed to three: direct collapse onto a massive black hole, runaway growth by a preferred lower mass black hole, and runaway collision, stellar collision in a stellar cluster, what I will focus today. Part of the problem of forming massive black holes is to fuel a large amount of gas to galactic nuclei. They also call feeding the monster problem because of the low angular momentum region of galactic nuclei is fueled by a order of magnitude larger angular momentum in gas in the galaxies. But simulations have shown that this is not such a big problem because in the local universe or in galaxy mergers or at high redshift, you can fuel huge amount of gas to galactic nuclei. So the straightforward question is, what will be the fate of such a gaseous material if it not end up forming a massive black hole or feeding a pre-existing one? Which physical configuration could be? Our approach to this problem is to study what we see today in galactic nuclei under the unified terminology of massive central object. Here I show you a mass and radius plot where black dots are resolved massive black hole candidates with their resolution radius and masses, and in red are nuclear stellar clusters with their effective radius and masses. We see that they are in two distinct parts of this graph, separated by this line that is not a whim, is instead when the average collision timescales equate to the age of the universe. So you can see that the simplest interpretation of this dichotomy will be that the precursors of massive black holes cross this collisionally relevant line, and the collisions happens everywhere in the cluster and will be stable to collapse into a black hole, and nuclear stellar clusters avoid such region. Nevertheless, this interpretation is not so straightforward because this compares the properties today of nuclear stellar clusters, not when they born, and they are expected to born much more compact in this region. And they are expected to expand and move in this direction as they evolve. The characteristic time scale for that expansion is the relaxation time scale, where I plot here in green, when this average relaxation time scale equates to the age of the universe, and we see that the two lines crosses, so we can see directly that there should be an unstable region where you have a collision timescale less than the age of the universe and relaxation timescale longer than the age of the universe. So the clusters here will not be able to be stabilized before they become runaway unstable. This intersection defines a mass scale from this triple equity, and it's also the same mass scale that you will find if you impose that the average collision timescale of the cluster is less than the age of the universe, and you couple it with the observed properties of nuclear stellar clusters. So only you should have survival clusters with less than this mass in agreement with the upper limit we observe. So this dichotomy inspired us to propose a scenario based on runaway collision for joint formation of massive black holes and nuclear stellar clusters. So basically, all the gas fueled to the center will be formed what the total mass in central massive objects. We will allow that all form stars, but the subsequent evolution of a cluster will make that some fraction end up being in a massive black hole and the rest in the nuclear stellar cluster. So, and all this is quantified by this black hole efficiency. For this scenario, we can look to the numerical simulations to see which numbers for efficiency we expect. Well, this should start at more or less 0.5, 0.1% for local global type clusters, but they should grow the black hole efficiency to up to a few percent for the case of a more favorable case of high redshift universe. Nevertheless, when you get to a point of larger clusters of more than 10 to the 7 solar masses, you expect that this efficiently dramatically grow. Why? Because for that number of particles, it's expected that no longer a three-body binary heating will be efficient to stop core collapse, and you will trigger runaway mergers. So this expectation from simulation can be directly contrasted under this scenario that assumes that the mass goes either to black hole or to nuclear star clusters that will have this kind of efficiency. We test this using the data from the review, the black hole masses and nuclear stellar clusters masses from the review of Neumayer et al. Of this year, and the black dot shows that, describing actually the expected growth in black hole efficiency at around few times 10 to the 7 10 to the 8 solar masses, and converging to unity for bigger masses. The upper triangles are lower limits in efficiency and are expected to move in this direction, and the lower triangles are upper limits in black hole efficiency and should move in this direction, suggesting that the trend in black dots is the correct one. If you want to hear more about this, and all the details are in the paper in Astro PH. Thank you.